So our final topic for the week is the second derivative test. So I'm going to state what it tells us. Let f be a function such that f prime of c equals 0. So it's a critical number, but it's only the critical numbers where the derivative is 0. And the second derivative of f exists on an open interval containing c. Part 1 of the second derivative test tells us if f double prime of c is bigger than 0, then f has a relative minimum at the point c f of c. 2, if f double prime of c is less than 0, then f has a relative maximum at cf of c. Now, the second derivative test is inconclusive if you get 0 for the second derivative. Okay. So I'm going to underline again, if your second derivative at c is bigger than 0, you have a relative minimum. If the second derivative is less than 0, then you have a relative maximum. And you just have to think in terms of concavity. Here, for the first one, if it's bigger than 0, it means it's concave up. Concave up means you have a minimum. Here, your second derivative is negative, so you're concave down. Concave down, you'd have a maximum. Okay. So let's look at a problem where we're going to use the second derivative test. I want to find the relative extrema of the function negative 3x to the 5th plus 5x cubed. Well, I have to find my critical numbers if I'm going to use that second derivative test. So f prime of x would be negative 15x to the 4th plus 15x squared. You could factor out a negative 15 and an x squared. So from this, I set this equal to 0. From this front part, you're going to get x equals 0. From this back part, x squared minus 1, you're going to get x equals plus or minus 1. So these are going to be your critical numbers. And because the derivative is 0 at these values, I can use the second derivative test. So now f double prime, second derivative would be, go back up here, take the derivative again, you'll get negative 60x cubed plus 30x. I can factor out a negative 30x, so it'll become a 2x squared minus 1. So now we're going to take each one of our x values, plug it into our original function. So if we plug in 0 into our original function, you get 0. If you plug in 1, you'll get 2. And negative 1, you'll get negative 2. So we're going to take these 3 points here and see what sign does our second derivative have. So I'm going to make a chart. Here's my points. 0, 0. So we'll start with -1, -1, -2, 0, 0, and 1, 2. And we're going to look for our second derivative. If I plug in x equals -1 into here, the sign will be positive. If I plug in 0 there into my second derivative, I will get 0. If I plug in 1 into there, it would be negative. So what does the second derivative test tell me? Well, if it's positive, right, that means it's concave up. So there's a relative minimum here. Here the second derivative was negative, which means it's concave down, so I have a relative max. And then here the second derivative was 0, so the second derivative test was inconclusive. So I don't know about this point 0, 0, so you're going to have to revert back to using the first derivative test on the point 0, 0. So go draw your number line. Here's 0. Pick 2 test points, and you need to stick pretty close to 0 because of your 1 and -1. -1/2 and 1/2. If you plug them into your first derivative, let's remind ourselves what our first derivative was. Is -15x squared. So if you plug in 1/2, it'll be a negative times a negative, so it'll be positive. It'll be also positive if you plug in -1/2. So at 0, the concavity doesn't change. So here, 0, 0 is neither a relative max nor a relative min. So I only had 2 points that were relative maxes and mins. So just to remind you, our relative minimum was the point -1, -2, and our relative maximum was the point 1, 2. And those are my relative extrema. So sometimes when you try to do the second derivative test, you get 0, which tells you that the second derivative test is inconclusive, and then you're going to have to revert back to doing the first derivative test.